Hello, George Notchik here. I had a viewer ask me how might I go about finding the equivalent resistance of this network. Many of you will realize that this is what we call a bridge network. That we have two legs and this is the bridge resistor. It goes between the two legs of the network. Now, what do we mean by equivalent resistance? That is, what we want to do is find a single resistance that could be connected between nodes A and D that has the same effect and the same value as this network does. Now, there's two ways that we can find equivalent resistances. Say we have a network. It can be combined of any number of sources, resistors, capacitors, inductors. And if we have two nodes accessible to this network, that say column A and D, can be any two nodes within the network, and we want to find the equivalent Thevenin impedance looking into that network. There's two things we can do. One, we can set all the sources within the network to zero. That is, we replace all voltage sources by a short, all current sources by an open, and then do a network reduction. Combine elements and get down to a single equivalent element that would be the impedance looking into the network. That is, we want to find Zn. And Zn in general, for both AC and DC circuits, has a real part to it, Rn plus J omega, I'll call this X in. That is, there's a real part, which we call resistance, and there's an imaginary part, which we call reactance. We can also look at the reciprocal of this as 1 over Yn, which is the admittance. And the admittance of a network is reciprocally related to the input impedance. Now, Yn can be written as Gn plus J omega Bn, where G we call conductance and the B we call susceptance. Now we're only going to be interested in this DC network. In a DC network, the omega goes to zero, so the reactances all go to zero. So we can replace inductors by shorts, capacitors by opens in the DC case to solve the network. Another way we can do this is take the network. We have the two nodes that we are accessing, and we want to find the equivalent impedance, Zn, looking in here. Well, what we do is we attach a voltage source to these two nodes, and we compute the current I in. And this is V, we'll call it Vn. We just activate the two terminals by a voltage source, compute the current In, and then Zn is Vn over In. Two ways we can do it. We can collapse the network down to a single equivalent impedance, or we can drive the network with a voltage source, find the current that we need to insert into the network. We call this the driving point impedance. This is the driving point. We're driving it with a voltage source, and we compute the current. Likewise, we could do something similar, and we could drive the input with a current source and then compute the voltage at the terminals and find the equivalent impedance looking in. We can call this Zn or Z equivalent. The equivalent impedance looking into a network between two nodes. Now, I'll use both methods for solving this network. I'm going to solve this network 5 different ways to illustrate different techniques that you can solve networks. I'm going to be using network reduction, where I'm going to introduce the Wye-Delta conversion to simplify the network. I'll use nodal analysis, mesh analysis. I'll do some Thevenin equivalents to simplify the network. And so I'll show you a whole collection of different techniques for solving the equivalent input impedance into the network. Now, to do a network reduction to find the equivalent resistance between points A and D, these two nodes, I'm going to use what's called the delta to Y conversion, or some people call the Y a star connection. What we have is, if we have 3 elements that are connected as a delta, like a triangle, then we can represent it as this Y or star connection, where we create a new node, which we call a neutral node, and say this is node A, this is node B, this is node C. Then we can replace the delta connection between those 3 nodes with a star or a Y connection with 3 impedances that have different values from the elements here. And to get the equivalency, the representation, say, of Z1, Z2, Z3 in terms of the ZA, ZB, Z3 in the delta connection, this is the conversion factors. Now, I define Z total in the delta network as the sum of the 3 elements, ZA, B, Z, B, Z3. And to go from the delta to the Y, it's very easy to remember this. Is, let's say here we have our delta element and another delta element here, and the other delta element is here. Okay, this is ZA, this is ZB, or ZC, and this is ZB. Well, Z1 is the product of the delta elements that are on either side of the Z1. So it's ZA times ZC over ZT. Z2 then will be the product of this element and this element, which is ZA, ZB over ZT. And the element Z3 is the product of these 2 elements, which is ZB, ZC over ZT. And if I want to go the other way, I define P as being the product of the elements taken 2 at a time, Z1, Z2, Z1, Z3, Z1, Z, or Z2, Z3. That defines P. Then to get ZA, what we have here is we take, this is my ZA, so we take the element that's opposite on the Y, which is Z3, and we divide that into P. To get ZA, ZB, now this one, we take the element in the Y connection that's opposite, Z1, and divide that into P. And then to get Z3, this element, we take the element opposite it in the Y and divide that into P. So these are the conversions. Now, we'll use that for, we recognize that this connection here between A, B, and C is a delta connection. I can write it in this fashion. I'll just redraw it. This is C, this is B, and this is A. This element has value 10. This is our bridge element of value 5, and this is the other element of value 5. So this looks like the delta. So the first thing we do is we find ZT. ZT is the sum of the elements 5, 5, and 10, which is 20. Then what I want to do now is convert this into a Y connection. Oops. So here's A, here's node B, here's node C. So I want to convert this delta into a Y. So here are my conversions. I want to find Z1. Well, Z1 is the product of 5 and 10 divided by ZT. So let's take 5 times 10 divided by 20, and we see 5 halves. So this value is 5 halves. What about this element? This element is 5 times 5 divided by ZT. So we have 5 times 5 over 20. 5 goes into 20 4 times, so we have 5/4. So this element is 5/4. And this element is 5 times 10 divided by ZT, or 5 halves. So that's our equivalent Y for this particular network. Now, what we're going to do here is replace this portion of the network, which is a delta connection, and represent it as a Y. So let's do that. So I'm going to redraw the network here. Here's node A, here's node B, here's node C. We didn't do anything with these two elements, so we have that element, which is 10. We have this element, which is 5, and here's node D. But between A, B, and C, now instead of having the delta, I'm going to put the Y connection in here. So and the value is 5 halves. This value is 5 halves, and this value is 5/4. Now remember, what we're looking for is the equivalent resistance between these two nodes. We want to find our equivalent looking in. Well, immediately we can see another reduction we can do in the network here. This element, these two elements are in series. These two elements are in series. Then those are in parallel. We can combine the parallel and then add it to this, which is in series, which I will do now. So I'm going to redraw the network. Here's A. This is 5 halves. Now I'm going to combine these two elements. 5/4 plus 10. Well, 10 is 40/4, so 40 plus 5 is 45/4. So I now have a branch here. This is 45/4. And then we're going to come to D. Now this branch is 5 halves plus 5. Well, 5 is 10 halves plus 5 halves, which is 15 halves. So those are the equivalents. I've replaced that series combination and that series combination. Now these two are in parallel. Well, with the parallel combination, we can either do the reciprocals that say 1 over R parallel is the conductances, the sum of the conductances, which is 5 or 4/45 plus 2/15. But 15 is 3 times 15 is 45, so this becomes 4/45 plus 3 times 2 is 6 over 45. that gives us sum over a common denominator, so we have 10/45. Well, 10/45, numerator and denominator both have a common factor of 5, so this becomes 2/9. So RP then is a reciprocal, or 9/2. So we can replace this now by a resistor of 9/2. So this parallel combination now becomes a single resistor of 9/2. So the equivalent resistance now, looking in, is the series combination of 5/2 and 9/2, which is 14/2, or 7 ohms. So our equivalent is 7 ohms. Now some of you might feel more comfortable, rather than working with conductances, to use the parallel formula. You know that if we have two resistors in parallel, call it R1 and R2, and we want to find the parallel combination, the R equivalent is R1 times R2 over R1 plus R2, but that's totally equivalent to the reciprocals. If we way I did it with the reciprocals, if I take 1 over R equivalent, this is R1 plus R2 over R1 times R2, where this is 1 over R1 plus 1 over R2. What we're doing is adding conductances when we do that. And that's what I did when I solved this. You can add the conductances and then take the reciprocal to get R equivalent. So we know now that the equivalent resistance is 7 ohms. Now I'm going to use method of mesh analysis and drive the nodes A and D with a voltage source, and use mesh analysis to find the equivalent current that we need to drive into the network, and then ratio the voltage to the current to get the equivalent resistance. Now, to do a network reduction to find the equivalent resistance between points A and D, these two nodes, I'm going to use what's called the delta to Y conversion, or some people call the Y a star connection. What we have is, if we have three elements that are connected as a delta, like a triangle, then we can represent it as this Y or star connection, where we create a new node, which we call a neutral node, and say this is node A, this is node B, this is node C. Then we can replace the delta connection between those three nodes with a star or a Y connection with three impedances that have different values from the elements here. And to get the equivalency, the representation, say, of Z1, Z2, Z3 in terms of the ZA, ZB, Z3 in the delta connection, this is the conversion factors. Now, I define Z total in the delta network as the sum of the three elements, ZA, B, Z, B, Z3. And to go from the delta to the Y, it's very easy to remember this, is, let's say here we have our delta element and another delta element here, and the other delta element is here. Okay, this is ZA, this is ZB, or ZC, and this is ZB. Well, Z1 is the product of the delta elements that are on either side of the Z1. So it's ZA times ZC over ZT. Z2 then will be the product of this element and this element, which is ZA, ZB over ZT, and the element Z3 is the product of these two elements, which is ZB, ZC over ZT. And if I want to go the other way, I define P as being the product of the elements taken two at a time, Z1, Z2, Z1, Z3, Z1, Z, or Z2, Z3. That defines P. Then to get ZA, what we have here is we take, this is my ZA, so we take the element that's opposite on the Y, which is Z3, and we divide that into P. To get ZA, ZB, now this one, we take the element in the Y connection that's opposite, Z1, and divide that into P. And then to get Z3, this element, we take the element opposite it in the Y and divide that into P. So these are the conversions. Now, we'll use that for, let's take, we recognize that this connection here between A, B, and C is a delta connection. I can write it in this fashion. I'll just redraw it. This is C, this is B, and this is A. This element has value 10. This is our bridge element of value 5, and this is the other element of value 5. So this looks like the delta. So the first thing we do is we find ZT. ZT is the sum of the elements 5, 5, and 10, which is 20. Then what I want to do now is convert this into a Y connection. Oops. So here's A. Here's node B. Here's node C. So I want to convert this delta into a Y. So here are my conversions. I want to find Z1. Well, Z1 is the product of 5 and 10 divided by ZT. So let's take 5 times 10 divided by 20, and we see 5 halves. So this value is 5 halves. What about this element? This element is 5 times 5 divided by ZT. So we have 5 times 5 over 20. 5 goes into 20 4 times, so we have 5/4. So this element is 5/4. And this element is 5 times 10 divided by ZT, or 5 halves. So that's our equivalent Y for this particular network. Now, what we're going to do here is replace this portion of the network, which is a delta connection, and represent it as a Y. So, let's do that. So I'm going to redraw the network here. Here's node A. Here's node B. Here's node C. We didn't do anything with these two elements, so we have that element, which is 10. We have this element, which is 5, and here's node D. But between A, B, and C, now instead of having the delta, I'm going to put the Y connection in here. So, and the value is 5 halves. This value is 5 halves, and this value is 5/4. Now remember, what we're looking for is the equivalent resistance between these two nodes. We want to find R equivalent looking in. Well, immediately we can see another reduction we can do in the network here. This element, these two elements are in series. These two elements are in series. Then those are in parallel. We can combine the parallel and then add it to this, which is in series, which I will do now. So I'm going to redraw the network. Here's A. This is 5/2. Now I'm going to combine these two elements. 5/4 plus 10. Well, 10 is 40/4, so 40 plus 5 is 45/4. So I now have a branch here. This is 45/4. And then we're going to come to D. Now this branch is 5/2 plus 5. Well, 5 is 10/2 plus 5/2, which is 15/2. So, those are the equivalents. I've replaced that series combination and that series combination. Now, these two are in parallel. Well, with the parallel combination, we can either do the reciprocals that say 1 over R parallel is the conductances, the sum of the conductances, which is 5 or 4/45 plus 2/15. But 15 is 3 times 15 is 45, so this becomes 4/45 plus 3 times 2 is 6 over 45. That gives us sum over a common denominator, so we have 10/45. Well, 10/45, numerator and denominator both have a common factor of 5, so this becomes 2/9. So RP then is a reciprocal, or 9/2. So we can replace this now by a resistor of 9/2. So this parallel combination now becomes a single resistor of 9/2. So the equivalent resistance now, looking in, is the series combination of 5/2 and 9/2, which is 14/2 or 7 ohms. So R equivalent is 7 ohms. Now, some of you might feel more comfortable, rather than working with conductances, to use the parallel formula. You know that if we have two resistors in parallel, call it R1 and R2, and we want to find the parallel combination, the R equivalent is R1 times R2 over R1 plus R2, but that's totally equivalent to the reciprocals. If we, way I did it with the reciprocals, if I take 1 over R equivalent, this is R1 plus R2 over R1 times R2, where this is 1 over R1 plus 1 over R2. What we're doing is adding conductances when we do that. And that's what I did when I solved this. You can add the conductances and then take the reciprocal to get R equivalent. So, we know now that the equivalent resistance is 7 ohms. Now, I'm going to use method of mesh analysis and drive the nodes A and D with a voltage source and use mesh analysis to find the equivalent current that we need to drive into the network, and then ratio the voltage to the current to get the equivalent resistance. Here is the original network, and we want to find the impedance, or the resistance in this case, the equivalent resistance between nodes A and D. So what we have here is node A and node D, and we want to find R equivalent. And from the Wye-Delta conversions, we determined that the equivalent resistance is 7 ohms. Now, I have the network here. Here's node A, here's B, here's C, here's D. And I'm now driving between A and D, the network with a voltage source. Now, what we want to do is find the current I1 that's driving this network and compute its value. And then our equivalent, looking in here, is just going to be V divided by I1. All right, I'm going to use mesh analysis. In mesh analysis, you write loop equations. We're using Kirchhoff's voltage law in each of the loops, independent loops. So I'll define the current in this loop. This is I1. The current in this loop is I2. And the current in this loop is I3. The directions of these loop currents is not important. It's entirely arbitrary, but once you select them, you have to stick with your definitions. Otherwise, you'll get all buggered up in your equations and you won't get the right answer. Now, loop 1. The first loop here, I'll call this loop 1. Designate it this way. Loop 1. We're going to write Kirchhoff's voltage law around here. So we have V is equal to 5 times, we have current I1 flowing through in this minus I2. So we have I1 minus I2 plus 10 times I1 minus I3. That's equal to V. Or if you sum the V on this side, it would be equal to 0. I'm just pulling the V out on the other side. Now, we can combine like terms. So we have V is equal to, we have an I1 and I1. 5 plus 10 is 15 I1. And we have a minus I2, minus 5 I2, and a minus 10 I3. Now, likewise, in loop 2, I'm going to do this in a shorthand method and show you how you do that. Is we're going to sum the voltages around the loop. So we'll have 0. There's no voltage source. 0 is equal to, for I1, in this loop, I2 is going to have the coefficient that's all the resistances that touch the loop current I2 minus the elements that touch the other currents. So in this loop we have a minus 5 I1. I1 is just touching the element of 5 ohms that's common to loop 2. And loop I2 has 3 elements, 5 plus 5 plus 5, or 15 I2. And I3 only is the element that's only common between loop 2 and loop 3 is element 5. So we have minus 5 I3. And for loop 3, again, there's no voltage sources here, so it's 0, equal to the element that's common to loop 3 and to loop 1 is 10. So we have minus 10 I1. The element common to loop 3 and loop 2 is 5. So we have minus 5 I2. And in loop 3, there are 5 elements that touch the current I3, which is 10, 5, and 5, or plus 20 I3. So here are our loop equations. We could write this in matrix form. We can write this as V0, 0 is equal to, we take the coefficients, we have 15 minus 5 minus 10 is minus 5, 15, minus 5, minus 10, minus 5, and 20. Let's do this as minus 10. Now, the thing to notice, and this is a good check on yourself, is that whenever you have a network that only has independent sources, no dependent sources, the matrix, the impedance matrix, will always be symmetric. I need to finish this equation. I've got to write this as another matrix, I1, I2, I3. Okay, so this is equivalent. This is the matrix representation of this system of three equations. We have V equals 15I1 minus 5I2 minus 10I3 for the next row. We have 0 is equal to minus 5 times I1 plus 15I2 minus 5 times I3, and so on. But the impedance matrix is always going to be symmetric when you don't have any dependent sources. That is, the off-diagonal terms are the same. Going in the off-diagonals, we have minus 5, minus 5, minus 10, minus 10, minus 5, minus 5. It will always be symmetric. Now, we can solve this with linear algebra. We can do row reductions, which I'm basically going to do here. So what I'm going to do now is I'm going to take twice this row, row 2, and subtract it from this, the first row. So if I go twice here, we can see that my I3 will drop out if I subtract twice this row from this row. So I'll write that out here. So writing, if I take twice this row and subtract it from this row, I get V is equal to, we have minus 10 subtracted from 15, so we get a 25 plus 25 I1, and then minus 45 I2. And the I3s drop out in that case. Now, for the next equation, next row, I'm going to add 4 times row 2 to row 3. If I add 4 times this, then the I3 also drops out, and we'll end up with 2 equations and 2 unknowns, in I1 and I2. So we're going to take 4 times this row and add it to this row. In doing so, I get 0 is equal to minus 30 I1 plus 75 I2. Now I'm going to simplify these 2 equations by taking out common factors on the right side of each equation. This equation I'm going to divide through by 5, so we get V over 5 is equal to 5I1 minus 9I2. In this equation I'm going to divide through by 15, so we get 0 is equal to minus 2I1 plus 5I2. I'm now going to multiply this equation by 2 and this one by 5 so that the I1s drop out when we add the 2 equations, and we end up with 1 equation in I2. So first equation, we have 2V over 5 is equal to 10I1 minus 18I2. Second equation, we have 0 is equal to minus 10I1 plus 25I2. We add the 2 equations. We have 2V over 5. The I1 drop out, and we have minus 18 plus 25, which is 7I2. Now, solving for I2, I2 then becomes 2V over 35. That's our I2. Now, we want I1. Well, we can go back into either one of these equations and solve for I1. This equation will be simpler because it's equal to 0. So let's solve for I1. 2I1 equals 5I2, or I1 equals 5/2 I2. But we just solved for I2. I2 is 2V over 35. So we have 2V over 35. The 2's cancel. 5 goes into 35 7 times. So I1 is equal to V over 7. But remember, our equivalent then is V over I1. So our equivalent then is V over I1, or 7 ohms. Just taking this equation, we'd have 1 equals to V over 7I, and for I1, or let's just do it a different way here. We want V over I1, so we bring the 7 over to the left, the I1 down. So 7 equals V over I1. So again, we get the same value as we did when we did the network reduction. Now I will solve this using nodal analysis. Now I've redrawn the network here, and again we're driving the network with a voltage source between nodes A and D. But now we'll use node voltage or nodal analysis to find current I1. Because what we want to find ultimately is our equivalent, which is V over I1. Well, in nodal analysis, we use Kirchhoff's current law at each of the independent nodes. So at node B, we will write currents leaving as positive. So there's going to be 3 currents leaving node B. Well, the current through resistor 5 is the voltage at B minus the voltage at A. So I'll write this as VB minus, well, what's the voltage at A? This is our reference node, so voltage at A is just the voltage between A and the reference node, which is V. So we have VB minus V divided by 5. That's the current in this resistor, plus the voltage across this resistor, which is VB minus VC, divided by the resistance, which is 5, plus the current through this resistor, which is just VB, the voltage from this node to the reference node, which is also the voltage across the resistor. So we have VB over 10, and that's equal to 0. Now, the other independent node C, we do the same thing. Again, currents leaving as being positive. Current through this resistor is the voltage at C minus the voltage at A, but VA is equal to V. I'll write that here. VA is equal to V. So, writing, we have VC minus V divided by the resistance, 10, plus the voltage across this resistor, in this case it's VC minus V, minus VB over 5, plus the voltage across this resistor divided by the resistance, which is VC over 5, is equal to 0. Now we can combine like terms. So in the first equation for my VBs, I have VB times 1 over 5 plus 1 over 5 plus 1 over 10 minus VC over 5, and then we have minus V over 5, which I'll put on the right side as a positive V over 5. I can multiply through by 10, so I have VB times 2 plus 1, or 5, minus 2 VC equals 2V. The second equation, let's combine terms. we have VC times 1 over 10 plus 1 over 5 plus 1 over 5 minus VB over 5 equal to V over 10. I'm just going to put, we have a minus V over 10 on the left side and put it on the right side. Again, I'll multiply through by 10. So I end up with ZC times 1 plus 2 plus 2, which is 5, minus 2 VB is equal to V. So these are our two node equations. I'll rewrite that up here. So our new two node equations, I have 5 times VB minus 2 VC is equal to 2V. And then I have minus 2 VB plus 5 VC is equal to V. Again, notice that if I wrote this in matrix form, that our coefficient matrix will be symmetric. That is, the off-diagonal terms will be symmetric. And that's also true for node analysis as it was for mesh analysis, that if you have a network with no dependent sources, the matrix representation will have a symmetric coefficient matrix. In this case, we call the matrix the conductance matrix because these values are conductances. Voltage times conductance gives us currents. And these are embedded current equations. Now, let's take, we want to either eliminate VB or VC, it doesn't matter which one. Let's just see, first eliminate the VC. So I'll multiply this equation by 5 and add it to twice this equation. If I do so, this equation multiplied by 5 is 25 VB minus 10 VC is equal to 10V. This equation times 2 is minus 2 VB plus 10 VC is equal to 2V. We add the two equations and our VC drops out. We can see that those cancel and we end up with 21 VB is equal to 12V. 3 is common to both 21 and 12, so we write this as 7VB is equal to 4V, or VB is equal to 4V over 7 volts. Now, we take VB and substitute it into either one of these equations to solve for VC. Let's just use the top equation. So we have 5 times 4V over 7 minus 2VC is equal to 2V. This is 20V over 7. Let's bring the minus 2V over, and that's equal to 2VC. Dividing through by 2, we get 10V over 7 minus V is equal to VC. Putting on the left side over the common denominator, we have 10V minus 7V over 7 equals VC. 10V minus 7V is 3V, so VC equals 3V over 7. Now, we're not done here because all we've solved for are the node voltages. We know the voltage now at node B and node C. The network is completely determined, but we have it determined in terms of node voltages, and we want to find current I1. Well, to find I1, we need to add the current through this resistor, 5 ohm resistor, and the current through this resistor. Basically what we're going to look for is, I will call this I1B and this I1C. So I1, so I1 then, which we're solving for, is going to be I1B plus I1C. And we know now that V at B is, we just determined V at B to be 4V over 7 and V at C to be 3V over 7. So now, using the node voltages, we can determine the currents in the 5 and the 10 ohm resistor. So I1B then will be the voltage across this resistor, which is VA minus VB, divided by 5. Well, VA is V, and VB is 4V over 7. We divide that by 5. V is 7 over 7, to put on a common denominator, minus 4, so this is 3V over 7 divided by 5, or IB1 is equal to 3V over 35. Likewise, to find I1C, I1C is the voltage across a 10 ohm resistor, which is VA minus VC divided by the resistance 10. Well, VA again is equal to V minus VC, which is 3V over 7 divided by 10. Well, V is 7 over 7 minus 3V over 7. So this becomes 4V over 7 divided by 10, or 4V over 70. Numerator and denominator have a common factor of 2, so this becomes 2V over 35. This is I1C. Now, I1 is I1B plus I1C, which is 3V over 35 plus 2V over 35, or 5V over 35, which is V over 7. Well, our equivalent is V over I1, and in this case, V over I1 is 7 ohms. Again, the same as what we had in the last two calculations. Now, the next way I'm going to solve this is using Thevenin equivalence. Okay, I've redrawn the network here, and again, I'm driving points A and D with a voltage source, and what we want to do is find the current I that's flowing into the network from voltage source V, so that we can compute the equivalent resistance. Our equivalent will just be V over I, and that's what we're looking for. Well, I'm going to play a trick here so that I can use Thevenin equivalence efficiently. And what I'm going to do is I'm going to add another voltage source of the same value as V. It doesn't change anything in the network. All the network voltages and currents will remain the same, no matter how many voltage sources of the same value I put in parallel with one another. Now, the difference is that there will be a current flowing from this voltage source, and the original current that I'm looking for, I, will be split. We'll call this current I1 and this current I2. So when I combine, my current I then will be I1 plus I2. I need those two currents. That's the total current that the voltage sources are driving into the network, which I need to solve for. Well, what I can do is whenever you have a voltage source connected between the same nodes, I can replace that short circuit with an open. It doesn't change anything. So now I have two networks that I can look at and reduce using Thevenin equivalent. The first thing I'm going to do is I'm going to replace this section with its Thevenin equivalent, looking into node B, and I'm going to replace this section with a Thevenin equivalent, looking in node C. So what I'll end up with is a Thevenin voltage, we'll call it VTH1, driving a Thevenin resistance at node B, and then I'll have my 5 ohm resistor connected between B and C, and the network on the right here will be VTH2 with RTH2. And then we have a series network. We can easily calculate the current then flowing into this resistor. And once we have that, we can back calculate then to get I1 and I2. So first let's figure out the Thevenin equivalent. The Thevenin equivalents, our first network, is this. This is node B, this is 5, this is 10, this is V. So the equivalent, Thevenin equivalent looking in, the first thing is we look at the open circuit voltage to get VTH. So VTH1 is going to be the open circuit voltage looking in at node B. Well, the open circuit voltage then is just the voltage divider, 10 over 15 times V. So it's this resistor over the sum of this and this, which is 15 V, or V over 2V over 3. Factoring out a 5 in the numerator and the denominator. Now, how about RTH? RTH1 is the equivalent resistance looking in to the dead network. So I replace V by a short, so we have 5 in parallel with 10 when I do that. So RTH will be 5 times 10 over 5 plus 10, which is 15, or 10 over 3. So that's the RTH. So this is 10 over 3. VTH is 2 V over 3. All right. Similarly, let's look this way. We have this network. And this is node C, and we have 10 ohms and 5 ohms in V. Now, looking in here, this is our TH2. And then we have the open circuit voltage of this network being VTH2. So let's first compute VH2. VTH2. VTH2 is just again the voltage divider. So we have 5V over the sum of the resistance, or 10, or V over 3. RTH2 is what? It's a parallel combination. We kill the voltage source, replace it with a short, so then we have 5 ohms in parallel with 10 ohms, and that's the same as RTH1. So that's 10/3. So VTH2 then is V over 3, and RTH2 is 10/3. So the current, we'll call it IBC. IBC then is, well, we'll just write a loop equation going around. So we have IBC times the sum of the resistances. We have 10 thirds plus 10 thirds plus 5. So we have 20 thirds plus 5, and then plus V over 3 and minus 2V over 3 is equal to 0. We're just writing Kirchhoff's voltage law around that loop. Well, combining these two, we have 15 thirds plus 20 thirds, or 35 thirds IBC, and then V over 3 minus 2V over 3 gives us V over 3, a minus V over 3, and I'll put it on the right side. So IBC then becomes V over 35. So this is the current that we want. Now, needs a little more work now. We have to go and now solve for I1 and I2. Okay, here's where we're at. We just solved for the current in the 5 ohm resistor, IBC, and we determined that IBC is V over 35. So now I'm going to draw some equivalent networks here. On this portion, I have voltage source V with 5 ohms and 10 ohms, but now I know the current leaving node B, so I can represent it as a current source with value V over 35 leaving node B and going to node C. And on this portion of the network, again, we know the current IBC, which is going into node C, so I'm going to write this portion of the network as voltage source V working into, oops, these are wrong. This is going into the 10 ohm resistor and then the 5 ohm resistor, but the current is going into node C, so the current source is sourcing current into node C with value V over 35. So we'll now solve these two little networks. We can use Kirchhoff's voltage law, just going around this loop. If I1 is coming in to this node, V over 35 is leaving, and the current going in this direction is I1 minus V over 35. I1's coming in, V over 35 subtracts from it, so the current in here is I1 times V over 35. So writing Kirchhoff's voltage law around the loop, I have 5 times I1 plus, that's the voltage across the 5 ohm resistor, plus the voltage across this resistor, which is 10 times I1 minus V over 35. And then we have a minus V, but I'll put it off on the right hand side as V. Okay, combining like terms, we have 15 I1 minus V. 5 is common to 10 and 35, so we have 2V over 7 is equal to V. Now, for this network, writing Kirchhoff's voltage law around this loop, we have 10 times I2, the voltage across this resistor. Now, V over 35 is sourced in, so I2 combines with this to go into the 5 ohm resistor. So I have plus 5 ohms times I2 plus V over 35. And then a minus V, which I'll put on the right hand side. Now, combining like terms, we have 10 plus 5I2, or 15 I2, and 5V times over 35 gives me a plus V over 7, and this is equal to V. Now, we can solve for I1 and I2 on these two equations. 15 I1 is equal to, bringing 2V over 7 and add to it V over 7V over 7, so we get 9V over 7, or I1 is equal to, we have a common factor of 3, and that gives us 5I1, which I can bring down to the denominator, so I have 3V over 35. On this equation, similarly, I have 15 I2 is equal to, I have 7V over 7 here, and then we're going to subtract the V over 7. So this is equal to 6V over 7. Again, I have a common factor of 3 on each side. So if I divide 3 here, I get 5, and I divide 3 here, I get 2. So my I2 then becomes 3, or 2V over 35. Now, I, which we're solving for, remember I is equal to I1 plus I2. So I is equal to I1 plus I2. I1 is 3V over 35. I2 is 2V over 35. So we end up with 5V over 35. Or I is equal to V over 7. Our equivalent is V over I, which is again 7 ohms. So we get the same value as we should. It doesn't matter what path you take. We're guaranteed, if you play the rules, by the rules, you'll always get the same answer. All paths, all roads lead to Rome. Now, I'll do one other analysis, do it using Thevenin equivalents, but in a little different way. All right, I've represented the network with its equivalent as I did before, where I've divided the network into two parts using the same voltage source driving each side of the network, and we've determined that the equivalent resistance is V over I, and where I is the sum of these two currents that are being sourced by the two voltage sources. Now, before, what we did is we isolated the network into two parts where on either side of the bridge resistor and represent it as a Thevenin equivalent. Now I'm going to go one step deeper in, and I'm going to represent the network and find its Thevenin equivalent on this part. Then doing that, I can find I2 by replacing this portion with its Thevenin equivalent, and then adding this portion of the network to it and compute I2. And similarly, I'll find the Thevenin equivalent for this portion of the network, and then attach V in the 5 ohm resistor to compute I1. So first, let's look at this portion of the network where we go up to node C. So representing the network, I've got V. I have a 5 ohm resistor, 10 ohm resistor. Then we have the bridge resistor. We're at node C. And then we have a 5 ohm resistor. Now I want to find the Thevenin equivalent of this looking in to node C. Well, first we have to find the open circuit voltage to get VTH. To find its Thevenin equivalent, I'll call it VTHA, or let's just call it VTH1, and then RTH1. Now these VTHs and RTH1s are not the same as on the previous module, the previous analysis, because we're deeper into the network. And then I'm at node C, and at node C we have a 10 ohm resistor, and we have voltage source V, and we're trying to find this current, I2. So now we can see we'll have a series network, and we can directly compute I2 this time once we know what VTH, the Thevenin equivalent resistance and voltage are for this portion of the network. Because I2 then, once we do that, I2 will be equal to, well, let's take it one step at a time here. If I write Kirchhoff's voltage law around this loop, we will see that starting here, we have V minus VTH1, and then our I2 is in the opposite direction as I go around the loop this way, summing. So this will be minus I2 times 10 plus RTH1 is equal to 0. So solving for I2, we will have V minus VTH1 is equal to I2 times 10 plus RTH1. So once we determine RTH1 and VTH1, we can solve for I2 because we know V. So that's what we're going to do here now. So VTH1 is the open circuit voltage. Well, the open circuit voltage here is the voltage at this node dropped by this voltage divider. So if I know VB in this case, then VTH1 will be VB times 5 over 10, or VB over 2. Because this is the voltage divider. It's 5 divided by the sum of the two resistors. 5 plus 5, or 5 over 10, or VB over 2. So if I know that voltage, then I have VTH2. Well, what is this voltage? Well, we consider it as being voltage V divided by this voltage divider, which is 5, working into this 10 ohm resistor in parallel with this resistance. Remember that RTA, if this is open circuited, these two series resistors work in parallel with a 10 ohm resistor and then forms a voltage divider. So we can do this one in our heads. The 10 ohm resistor is in parallel with a 10 ohm resistor, which means the equivalent resistance is 5. We have an equivalent resistance of 5 ohms here and a 5 ohm resistor, so VB will just be V over 2. So V over 2 times 1/2, this is V over 5, or V over 4. That's our VTH1. So VTH1 is V over 4. Now, how about RTH? Well, RTH is the equivalent resistance looking in here when we kill the voltage source. If we kill the voltage source, we have our 5 ohm resistor in parallel with the 10 ohm resistor, which is in series with the 5 ohm resistor, and that will be in parallel with the 5 ohm resistor here. So we have, this is the equivalent resistance looking at the equivalent network when we kill the voltage source V. So 5 in parallel with 10. A 5 ohm resistor is the same as two 10 ohm resistors in parallel, and then in parallel with another 10 ohm resistor gives us an equivalent resistance of 10 over 3. So I can replace that with 10 over 3. And 10 over 3 is in series with the 5 ohm resistor. Well, the 5 ohm resistor is 15 over 3. We add it in series with 10 over 3, so the equivalent resistance here is 25 over 3 in parallel with 5. So I will rewrite this as, we have a 5 ohm resistor, and we have a 25 over 3 ohm resistor, and now we want to find the equivalent resistance looking in. Well, the equivalent resistance is the product of the two resistors divided by their sum, or we can look at the reciprocals. I will look at the reciprocal. So 1 over R equivalent then is the sum of the conductance of this resistor, which is 1/5, plus the conductance of this, which is 3 over 25. 1/5 is 5 over 25, so this is 8 over 25. So R equivalent then is the reciprocal, or 25/8 of an ohm. So RTH1 is 25/8. Now, let's solve for our I2. Well, V minus VTH1 is V minus V over 4 is equal to I2 times 10 plus 25/8. Well, 10 is 88 plus 25/8, which is 105/8. And V minus V over 4, this is V over, or 3V over 4. So this becomes 3V over 4. Now, I2 then is 3V over 4 times 8 over 105. 4 goes into 8 twice. 3 goes into 105 35 times. So we have 2V over 35. So that's our I2. I'll write that up here. This is 2V over 35. Now that we've solved for current I2, we need to now find current I1. Well, to determine I1, we replace this part of the network with its Thevenin equivalent, draw the equivalent network, and solve for I1. So, what we're going to have here, then, is this. We'll have voltage source V with the 5 ohm resistor. We'll be at node B, and then we replace the remaining network with its Thevenin equivalent. We'll call this VTH2 and RTH2. And the current then flowing through the 5 ohm resistor is I1, which we're going to be solving for. And this is a simple series network. We can write our equivalent here is summing Kirchhoff's voltage law around the loop. We have I1 times 5 plus RTH2 plus VTH2 minus V is equal to 0. In solving for I1, I1 then will be equal to V minus VTH2 over 5 plus RTH2. So we need to determine, we know V, we need to determine VTH2 and RTH2 to solve for I1. Okay, well, let's look at our equivalent network. Our equivalent network looks like this. First, we extract the portion of the network that we're going to get our Thevenin equivalent of. So this is node B, this is 5, this is 10, this is 10, this is 5, and this is V. So we want to find the equivalent, Thevenin equivalent, looking in there. Well, looking in here, there's node C. We first want to find VTH1, which is, or VTH2, which is the open circuit voltage across the network here at the 10 ohm resistor. Well, we note that the voltage across at B, between B and the reference node here, this voltage is a voltage divider. If we know the voltage at node C, then it's just a simple voltage divider to get the open circuit voltage, VTH1 or VTH2. So VTH2 then will be the voltage at C times the voltage divider. Well, the voltage divider here is 10 over 10 plus 15. So 10, or 10 plus 5. So that's 10 over 10 over 15, or 2 VC over 3. So now to determine VC, we note that we have a series parallel combination. We have two series resistors in parallel with a 5 ohm resistor. So we're going to replace and have our equivalent network. We have a 5 ohm resistor. This is node C. And then in parallel, we have 10 plus 5, or 15 ohms. And then this is hooked to a voltage source V. Now we want to find the voltage here. Well, we note that a 5 ohm resistor can be thought of as 3 15 ohm resistors in parallel. Whenever you have n resistors of the same value in parallel, the equivalent resistance is just R over N, divided by how many resistors are in parallel. So we will place the 5 ohm resistor, say, by 3 15 ohm resistors. And to it we add another 15 ohm resistor. So we have 4 15 ohm resistors in parallel. So this parallel combination is the same as having a single resistor of value 15 fourths. And to that, we have a 10 ohm resistor which forms a voltage divider. So then VC will be equal to V times 15 fourths divided by the sum of 15 fourths and 10. But 10 is 40 fourths plus 15 fourths gives us 55 fourths. Or this becomes 15V over 55, or 3V over 11. That's our VC. Now, we put that in here, so we get VTH2 is 2/3 VC, which is 3V over 11, or 2V over 11 is our VTH2. So this now becomes 2V over 11. Now we need to find our Thevenin equivalent resistance. Now that we found VTH2 to be 2V over 11, we need to find RTH2. Well, here is our equivalent network. We need to find our Thevenin resistance looking in to node B. Looking in this way, we're looking for VTH2. Well, we kill the voltage source, meaning we set the voltage source, the dependent voltage source, equal to 0, and replace it with its internal impedance or resistance, which is a short circuit. So what we have here then, at B, we have 10 ohms, we have a 5 ohm, and then a 5 ohm, and a 10 ohm in parallel. Well, we have and we're looking to find RTH2. Well, we have, looking in here, what we have is this parallel combination in series with this parallel combination in parallel with 10. So let's replace this by its equivalent. A 5 ohm resistor is the same as having two 10 ohm resistors in parallel. So we have 3 10 ohm resistors in parallel, and that is equivalent to the combination. If you have n resistors in parallel, the equivalent value is the value of the resistance of any one resistor divided by the number of resistors in parallel of the same value. So in this case, this is 10 over 3. So we have 10 over 3. And that's in series with the 5 ohm resistor, which is in parallel with 10. So now this becomes, if we add the 5 ohm resistor to the 10/3 ohm resistor, this is the same as 15 thirds plus 10 thirds. So We replace it with an equivalent resistance of 25/3. And these two are in parallel now. Well, the parallel combination here, so RTH2 is the product, 10 times 25 over 3 over the sum, 10 plus 25 over 3. Multiplying numerator and denominator by 3, we have 10 times 25 over 30 plus 25. So this becomes 10 times 25 over 55. We have a common factor, numerator, denominator of 5. So this is 2 times 25, or 50 over 11. That's our RTH2. So the equivalent resistance here is 50 over 11. Now, putting into the equation, we have V minus VTH2. VTH2 is 2V over 11, so we have V minus 2V over 11 divided by 5 plus RTH2, or is 50 over 11. Multiplying numerator and denominator by 11, we have 11V minus 2V over 55 plus 50, or 9V over 105. 3 is a common factor, so we have 3V over 35. That's our I1. So I1 is 3V over 35. We're almost there. Now we get our current I. I, remember, is I1 plus I2. So I is equal to I1, which is 3V over 35, plus I2, which is 2V over 35, which is 5V over 35, or V over 7. So R equivalent is V over I, or again, 7 ohms. So again, we get 7 ohms. It doesn't matter the method in which you use to solve a network, as long as you follow the rules and don't make any mathematical errors, you're guaranteed to get the same value. This is called the uniqueness theorem. In a linear network, there is one and only one solution, and it doesn't matter how you solve the network, what path you take. You can sort of think of this as being a conservative system in a sense. It's path independent. Now, the next network problem I will be solving in the next network video will be the use of superposition in solving network problems when you have multiple sources within your network. We'll be using the superposition principle for solving the network.